Hello, everyone. Thanks for joining us for our monthly new bioenergy webinar. This month we have an excellent presentation, and I thank you for taking the time out to join us. I'm Mike Jacobson, professor at the Department of Ecosystem Science and Management here at Penn State, working on the extension activities with the new bio project. If you're not on our mailing list, please get on it and you'll get a lot of good updates. I'm helped here by Sarah Wurzbacher, who's an extension educator working on the project as well. So today we have Dave DeVallance as our speaker, and Dave is assistant professor and program coordinator for wood science and technology at the Division of Forestry and Natural Resources at West Virginia University. He got his BS in wood products from Penn State. That's good to see. He was out in the real world working on engineered wood for a corporation, and then he went to get his his master's and PhD in wood science from Oregon State, finishing up in 2009, and then he's been at West Virginia ever since. So as you can tell, he works on wood products related issues, and his areas of research include obviously pellets and biomass, which he's going to talk to us about today, but he also works on cogeneration of biomass and developing bio-based composite materials. You know, this idea of mixing wood product material with other types of stuff like plastics. So Dave's topic is to talk about wood pellets, and the global environment. So without further ado, I'll turn it over to Dave. And please post your comments and questions in the chat box, and we'll get to them after his talk. Dave, it's all yours.
Okay, thanks, Mike. I'm assuming everybody can hear me, and if you can't, you'll be typing things in the chat box soon to tell me to speak louder or that you can't hear me. Okay, so again, I'm David DeVallance. I'm a assistant professor for about the last 4.5 years at West Virginia University, and as Mike said, I'm focusing on a few different topic areas, but really my main background and main research background has been wood-based composites, densification of wood materials, which has led me into looking at bioenergy type materials in terms of, at least what we're going to talk about today, densification of a wood type product or a biomass type product into an energy fuel. Let's see, make sure I can get the slides going here. Okay, so what I'm going to talk about today is I really wasn't sure exactly who all would be coming on here to listen to me for the next 30 or 40 minutes. So I kind of mixed in a little bit of just general background on pellet manufacturing, and then on pellet quality and properties and pellet markets. So I tried to mix in a little bit of things in terms of general overview and how these different terms from the manufacturing side influence pellet production and pellet quality, but then mixed in a little bit of my research background and research that myself and some colleagues here at West Virginia University have been doing to come up with some of these numbers. So my strong point or strong suit is really in these first two things, the pellet manufacturing and the pellet quality and properties. But I was also asked to talk a little bit about markets, and I do have a few students working on marketing aspects, really more towards coal, biomass to liquid fuel markets. But I do follow the pellet market trends a little bit. So I put in some data, mostly data that other people have put out for people to look at, just to look at some of the regional and global trends and where we're making these pellet materials and where they're going. So the first one I'm going to start with is pellet manufacturing, looking at feedstocks, additives, and processing parameters. Okay, so I just have up here a general flow. See if I can get the pointer to work here. Okay, so the general flow going from wood chip delivery to wood chip storage all the way through the different processing steps. The ones I'm going to talk about today are going to be looking at chipping a little bit, and then moving into grinding or using a hammer mill, and then after that drying, and then conditioning if you need to, and then going in down through the pellet mill. So I'm going to look at a few of these things, but focus mainly on the major steps in terms of pellet manufacturing. I'm not going to get too much into storage and cooling and packaging and transportation, but those are all areas which are very important too. I just don't have the time to go in those today. Okay, so here's a general flow. You can see materials flowing in through this process, and the first thing I'm going to talk about is going to be feedstock characteristics, additives, and processing parameters. So if I look at just feedstock and pre-processing, I broke the talk down into materials and species, and I'll hit just a little bit on species, but then move into grinding, what we need to do in terms of particle size and shapes, and then looking at moisture content and how that influences pellet quality. The next section I'll go through is just some things on additives and pretreatment. So I'll talk a little bit about binders and lubricants, but then get a little bit more into some hot water extraction, pretreatment methods, and torrefaction. So really the focus of the some of the area that I've been working on here at West Virginia University has been particle size and shape, and looking more so at this hot water extraction and torrefaction section. Then finally, on the processing side, look at once you start making pellets, looking at temperature, steam addition, or what temperature you need to be at. And then general thing on just die dimensions, die speed, gap between the roll and die, and feed rate. So mainly looking at these from a processing standpoint and how these process parameters influence the final quality of the pellets that we're going to be making. And I recently purchased a lab scale pelletizer which scales up pretty well to an industrial size, and the things I've been researching with that piece of equipment have been these areas here. Okay, so I want to start off with just looking at feedstock availability, and right now in terms of residues, there's been a lot of potential, a lot of work looking at just using forest residues and mill residues in terms of making or getting the feedstock for making pellets. So this first graph in the United States just shows different areas in the U.S. where we have a lot of resources available in terms of biomass forest residues. Okay, so we see a lot out west, the southeast, northeast, a little bit up in the Midwest, places you would think there should be some forest residues. The next one is looking at primary mill residues. So this is looking at things coming from like lumber mills, veneer mills, any place where they're producing a primary wood product, and then they have waste left over and can use that for other areas. So a lot of this is going to be centralized or located around the wood products producing regions of the United States. And you can get an idea of how many dry tons per year in each of these regions we can get in terms of primary mill residues. The next one is secondary mill residues in the United States. So this is looking more at the secondary operations. So it could be furniture type operation, molding, millwork, anywhere where that isn't dealing with traditional logs and producing lumber out of those. So somebody taking those materials and doing a secondary operation on those type of wood materials. So these are secondary mill residues, and you can see a little bit different. They're a little more scattered out, at least in the Midwest and in the South and down into California than were the primary mill residues. Last one is has a little bit of attention placed on it as urban wood residues. So I know was recently at a meeting where they're talking about the Seattle Steam Company up in Seattle was using nothing but urban wood residues to run a boiler to produce steam for the city. And so there are, places in the United States where we do have a large concentration of urban wood residues that could be potential feedstocks for producing pellets. It gets a little trickier with some of these materials in terms of just dirt and particulates and things you don't want in there necessarily if you're trying to make pellets with low ash concentrations or low sulfur. So one last thing on wood residues. So we break these down into primary and secondary, which I talked about. So in the primary section, we can have logging residues, we can have fuel treatments, we can have tree trimmings that come off of a site. And so a lot of these are going to, be materials with a lot of maybe limbs, branches, leaves possibly, but they're going to be things that aren't typically taken out in terms of feedstock for going into a lumber production or veneer producing type situation. Secondary wood residues, primary wood processing mill residues, secondary wood processing mill residues. We won't really deal much with pulping liquors in this case, unless we're looking at taking some of the lignin or lignin byproducts off to produce a binder for pellet materials. And then the tertiary wood residue is again the urban wood residues. Okay, so we have a variety of wood forms that we can use for pellet feedstock, and so I just put a circle around the most common ones. Typically most common ones would be chips. Flakes in this case I have is wood shavings, and then particles or sawdust are going right into particles. There's been some increased activity in using logs and actually bringing in logs, chipping them up, and then putting them through a hammer mill and producing the particles you want. And at least in the region where I'm at in West Virginia, the downturn in housing and furniture production and things like that have fueled a little bit more of using these type of log materials. Once sawmills start shutting down, there's more availability of these hardwood saw logs, a lot of times the lower quality saw logs, and things like that that can be actually purchased for a decent price and turned into chips. Okay, so you can get an idea of just the size. We go from logs down to lumber veneer to flakes and chips. When we get down to wood flour, these would be more things that would be used in case of wood plastic composites, and then cellulose in terms of cellulosic nanocrystals or even cellulose for bioethanol plants and things like that. So we're up here in this particle region where we really want to be for producing wood pellets. Okay, so we bring in this raw material, and a lot of the raw material we bring in is going to have different chemical compositions which are going to impact whatever resulting properties we're looking at in terms of the kind of pellets that we want to make. So a lot of times we'll go through, even on the particles that we here in the lab or a mill, where we bring in, go through and classify the amount of nitrogen, sulfur, and chlorine in these materials, because they can be potential problems during combustion in terms of pollution potential that they have. So you kind of want to try to pick a feedstock where you minimize some of these things. Chlorine can also lead to metal corrosion. So this is a property that's looked at pretty closely by the pellet fuel industry. You don't want to start corroding your pellet stoves, things like that. So chlorine is one of the things that's actually measured very, very frequently and kept to a minimum. And we have different feedstocks that are going to vary in ash content. And really, if we look at feedstocks, when I talked about materials and wood materials before, we have different hardwood, softwood species. So a lot of times we'll get questions on what is the difference between using hardwood and softwood for pelleting. Is softwood pellets better than hardwood? And a lot of it just depends even on species, not necessarily hardwood versus softwood, but just the actual properties of those wood materials. So in general, softwoods may have a little more higher resin content, so they could burn a little hotter, a little faster. The ash content can vary So you could have hardwoods that are very high in ash content and low, and the same with softwood. So it's more really just species dependent in terms of these properties, and not so much the whether or not it's a hardwood or softwood. So we had done some research between yellow poplar and red oak in terms of pelleting, and they had similar surface properties, but when we made the yellow poplar pellets, they had a much lower strength. So other things factor into pellet properties other than just these chemical compositions. But if we start looking at some of these compositions and we look at, say, poplar, you can get an idea of how much chlorine is in poplar and willow wood chips and spruce versus something like grasses or miscanthus and grass. So you can get a lot higher chlorine level depending on what, if you're pelletizing a miscanthus type material or a grass type material versus if you're pelletizing something that comes from a wood type product. The same thing follows along with the sulfur content and nitrogen content. Really, one big thing that we measure for using, in our case, we use a ultimate analysis test and want to look at how much ash content there is in these materials. So if we look at hardwood and softwoods, they can be 1% and below. You can get over 1% in some cases in terms of ash, especially once you start adding bark in, then you're getting up a lot higher in terms of ash. So if you're producing wood chips and you're not debarking the logs really well, then your ash content can go up. So we really look at debarking logs as something that can really play an important role in terms of the ash content. If we compare that to, say, perennial grasses with infield leaching, 4 to 3 or 3 to 5% ash content, or switchgrass, which is sort of around 3. So wood, in terms of ash content, is relatively low in compared to some other biomass materials. Okay, so once we take these raw materials, we have to process them down into some particle size. So particle size is going to be really important for particle densification, or chamber packing, and energy required to make these pellet type products. So the first thing, if we're taking logs, we can do some infield chipping. This is some chipping that was being done in Nebraska. I was out there working on a biomass feasibility study, 3 of those for biomass boilers, and this is really agricultural land, and they were clearing just some trees they had on this agricultural land, and these chips were actually going to a community college to heat a chip-fired boiler. So we have to reduce, in terms of pelleting, reduce these log or larger materials down. So it could be done using chip vans and portable chippers, or it could be done at the actual pellet mill itself. In terms of chippers, typically see a drum, disc, screw or wheel type chippers. And then after we go through the chipping process, we need to do something to get those chips down to the kind of finer sizes we want. So the typical type of grinding or particle size reduction is done by either a hammer mill or a grinder, with probably a hammer mill being the most prevalent. In terms of chips, there are different size chips. Some people are developing microchips, or machines that can make microchips that make hammer milling and grinding more efficient. But we don't always have to get everything down through a hammer mill and reduce its size that way. If we have sawdust, and depending on the size of our sawdust, you may not need to actually reduce this much more. But if we're looking at shavings like planer shavings or mill shavings of some sort, then we might have to put them through a hammer mill or grinder. But they're much less energy intensive than, say, chipping using a log or running chips then through a hammer mill. Okay, so why do we care so much about particle size? So this is an area that I focus and have a lot of students focusing on, is densification and flow and mechanical properties of pellets based on particle size and energy and how they flow into a die. So particle size is really important in terms of flow and mechanical interlocking aspects during the pelletization process. So I have two just crude diagrams or illustrations I put up here. If we have large particles, like we have in the corner up here, you can see you can get more flow. So you have a lot more void space. It's easier for particles to get in here and flow down through the chamber. It's easier to pack these in here. But however, you don't get them packed as dense. So when you get smaller particles, you get less flow of the material into that die. What that causes is you need more energy in terms of actually packing this and producing a pellet or pushing material through this die. But what it does make for are more durable pellets. So you have a lot more surface area, and you can get a lot more interlocking, get a lot more contact, a lot higher surface energy. So you can start producing materials that are have a lot higher density, a lot less airspace, but again, there's higher energy requirements. So if we look at, for looking at something other than particles, say we're looking at fibers, so you could take these wood chips, you could put them in a grinder or a disc refiner, a wet disc refiner or a dry one, and you could actually produce fibers. They would make really good pellets. This is what we do if we're making fiberboard for making wood products or wood panels out of wood. We make a lot of fiberboard panels, and you can make pretty tough pellets doing this. You get a lot of mechanical interlocking with these type of fibers. However, it's really hard for the kind of pelleting systems that we're used to or we use. So we're more interested in this kind of particles in order to put them through this die. So we have a target size if we're looking at a 6mm diameter pellet, which is a common pellet size, so maybe about a 1/4 inch pellet that would be used in typical home residential heating. We're looking at a particle size about 4mm is our target. So we'll have things a lot lower and higher, but on average we try to want to stay around 4mm. Okay, so that's all I'm going to talk about really on particle size and shape. I could probably spend the entire webinar just talking about that. But really what the next step I want to talk about is moisture content and how this affects the pelleting process. So when we're doing or making pellets, we need to continually look at the moisture content and adjust it. It influences a lot of things. One thing it influences grinding energy and also pelletizing. So typically if we get sawdust and planer shavings in, it's going to hopefully be dry unless it's been sitting out for a long time. So we don't do too much in terms of hopefully drying those things down. Wood chips, on the other hand, generally need to be dried. They contain both free water and bound water. So bound water is going to be the water that's in these wood chips below the fiber saturation point that's bound in the cells. It's harder to take out. Free water comes in and out pretty easy once the bound water fills up and these are saturated. So it takes a lot of energy to get this water out, especially once it gets down into the bound water range, get that water out of these chips. So we can do different types of drying. Natural drying helps because it's free. Let these wood chips sit out for a while and reduce their moisture content of their own. But if we waited just for natural drying, processing would probably take quite a while. So we do a lot of forced drying. So we have tube type dryers, drum, belt, low temperature, and superheated steam. So a lot of these dry in different ways. A tube is more indirect heating at about 90 degrees Celsius. A drum can be 300 to 600 degrees Celsius. A belt might run at the inlet temperature about 90 to 110 degrees Celsius, and then coming out at 60 to 70 degrees Celsius. And then low temp really runs 50 to 100. And then what happens with this low temperature dryer is the dry particles kind of drop out of the system as they get dried. And then superheated steam is something that people are interested in for a fast throughput. Sawdust can take 10 to 20 seconds to go through a superheated steam system and be dry. So why do we really care about moisture content? Really because we're using, at least in our case, wood. The moisture content acts to promote binding and provides lubrication. So really what we're looking at with wood products in terms of making pellets is looking at using lignin. And using lignin to, one, soften and sort of melt and then bind these particles together. So in terms of wood, the glass transition temperature for wood lignin is about 170 degrees C. We can adjust that depending on what moisture content we're at. So this diagram over here has the glass transition temperature versus water content or moisture content. And we see as we get higher in moisture content up in this region, our temperature at which we need to be at to soften the lignin reduces. So if we're up at 1% moisture content, we really have to get that temperature high in our pellet die in order to start plasticizing that lignin and helping with our bonding. So if we're looking at what moisture content we should be at, I've seen various things in terms of this. In terms of the optimal one, anywhere from 6 to 15 has been shown in the literature. Other people say 12 is the max moisture content you should have. I've seen 8 to 12, but really a lot of times I try to stay, when I'm doing my stuff, stay up towards 12 and try to lower that die temperature that I need to be at. If we're looking at corn stover or switchgrass, they have a glass transition temperature of about 75 degrees C when we're at a moisture content from 10 to 20. The next section in terms of processing is we go from taking these particles that have been dried and treated and start adding additives to them. So the first one, if we need to, we add some kind of binder. So lignosulfonates, starches and flours, shells. We can add some molasses in some cases. Vegetable oil mainly acts as a lubricant. Helps us reduce the energy it takes to force that thing through a die. And then the next part of this is steam and water pretreatment. Okay, so here we're adding things over here to improve the properties. Here we're actually pre-treating either the chips or the particles in order to improve their bonding capability and, in a lot of cases, their durability once they become a pellet. So we use superheated steam treatment and hot water extraction. And here's just some examples of some studies we've done. We did some hot water extraction at various levels, but these two pellets were same raw materials. This was hot water extracted at 170 degrees for 45 minutes prior to making pellets, and this one was just raw wood particles pelletized. And you can see after soaking these pellets for 20 seconds, they've pretty much come apart. When we use a hot water extraction process, we soak these for 20 minutes, and you can see the pellet here is still pretty well intact. So you can do things in terms of removing, in this case, hemicellulose to improve its durability. The next thing is torrefaction. This is gaining popularity and it's heating of feedstock. These temperatures vary, but 200 degrees Celsius to 300 degrees Celsius in an atmosphere free of oxygen. So you can see some torrefied pellets up on top. They turn black, have a high carbon content, properties closer to what you would find in coal, and they're said to be hydrophobic. Okay, they tend to not take up water as much. So we've done some studies on that. I don't know how easy it is to see, but over here, these bottom three are some torrefied pellets that were submerged in water. Here's raw wood in water. And you can see down here as the torrefaction level increases, they take up a lot less moisture as you soak them in water. So they're not completely hydrophobic. they do take up some water, but not as much as, say, raw wood or non-treated wood would. Okay, so we move through these pre-treatment processes and look at the type of pelleting that we typically see. In general, there's two types of common type of pellet mills, a ring and a flat die type. The ring die type is probably the more common industrial one, and that's over here. So we have this ring, it's inside this machine, then you have a set of rollers that are going around while the die is also turning, and the feedstock's getting pushed through these dies and comes out and gets cut off. So that's the ring die type. Different kind, the kind that I do have in my lab, and they also have on industrial scales, is a flat die, whereas now you don't have this moving ring, it's just a flat die, and these rollers are what are moving around in the circle. So feedstock comes in, gets underneath here, and starts getting pushed through these dies. So some key processing parameters in making pellets is temperature. As we discussed before, we really want to get that lignin to soften. If we're looking at a typical pellet mill, the temperature inside there gets about 80 degrees C to 90 degrees C if you're at 12% moisture content. So for lignin softening, it's still, in a lot of cases, a little too low depending on what material we're looking at. So if that happens, we use steam a lot of times to help soften the lignin and raise this die temperature. And one thing that it can cause, though, if you have too much steam, you can get in slipping of the die. You actually get a situation where none of the material is really flowing through the die well, and it builds up, and it can actually, at least I see this all the time in my case, it actually stops the die from going around, and you build this big layer of non-pelletized layer through there, and it's really hard to get anything to go through those dies. In terms of the dies themselves, we have this chamfered area where the material is going to flow into, and we really don't start doing anything in terms of compression until we start getting material through here. So we look at the length to diameter, or L over D ratio, of your die. So you can put different thicknesses of dies in your process. And for woody biomass, we're looking at a range from 3 to 5. Grasses, about 7, and ground corn, they recommend about 12. So this is what happens in the die. So you have this roller, your feed comes in, and you start, as this roller rotates this way, your die is going this way in terms of the ring type. You start forcing that material down through these channels. So a lot of things play a role in that, like the gap between. So how much gap do you have in here between the die and your roller? How fast are you feeding that material in, and how fast your die is going around. Okay, so that's a general overview just of the manufacturing process. And I just want to spend a few slides just talking about, we talked about all these things you do in processing that affect quality. So just a couple slides on what are the expected qualities of a pellet, and who looks at these, and who puts together the standards for these type things. Okay, so if we're looking in the United States, most pellets are evaluated using the Pellet Fuel Institute's Residential Commercial Densified Fuel Standard. So you can see they have 3 different levels: premium, standard, and utility. And then they have a bunch of different properties that you test for, and a lot of them are based off of ASTM standard methods, or some kind of modified ASTM method to fit whatever needs for this specifically. In terms of the main things we're looking at here, ash content. So if you're looking for a premium pellet, 1% is the maximum ash content. The other one is pellet durability. We measure this by putting pellets, a certain amount of pellets, and turning them in a bin, a container, and see how much is still intact. But there's requirements on density, diameter. In terms of the PFI standards, there's nothing on heating value, but there are things on chlorine and moisture content. So we've been looking at this certification and standards a little bit recently, and noticed that there has been some movement in looking at standardizing this and getting third-party certification. Like we do this on a lot of other wood products. Structural panels, for instance, are accredited by an outside third party. This is the same kind of thing. So you have a standard. It's made by PFI. You have American Lumber and Standards Committee that enforce this. You have accredited testing agencies that will go and give you the properties, test for those properties, and then you get a stamp like this, or a logo that you can put on your bags or whatever. And it just gives you what the properties are and what grade those are. And on their website they had said that there's currently 4 accredited companies under this standard program. In Europe they have a similar type program and standards. They have a handbook for wood pellets. It's called EN+, and you can see here's the highest grade. You can see the ash content in this case is a little bit lower than what we require for premium grade here in the US. But there's, again, the same thing, different levels and different grades. One thing that's a little different, they do give you a net calorific value. So you would determine the higher heat value, or megajoules per kilogram, or BTU per pound. And they also look at nitrogen and sulfur, and still chlorine, obviously. So their standard's a little bit different. So why do we brought up the United States standards and the European standards? So I'll finish off the webinar today talking about pellet markets and regional and global trends. So in terms of regional, I'll focus mainly Northeast a little bit, but kind of just typical over the United States. Global is going to be more looking at global trade, and I brought up Europe because that seems to be the largest market for wood pellets produced in the United States. So I'm really going to focus here more on the European market. So if we're looking at the United States, where are our pellet production facilities located? So you can actually get on and if you Google Pellet Map, Pellet Mill Map, you can get on and start looking at different locations. So here's the whole United States. Gives you an idea of the concentration of mills in the different regions. And then you can start zooming in, zoomed into the Northeast area, West Virginia, Pennsylvania, of course. Then you can get in finer. Here's West Virginia, and here's Morgantown, where I'm sitting today. There's one pellet mill up here, and then in West Virginia we have 3 pellet mills fairly close. And then if you get really nosy, you can start zooming in and figuring out, in a lot of cases, where these pellet mills are exactly located, what they look like. You can see, they have some, looks to me like some packages of pellets sitting out here, some raw material over here, and you can look at things like that. So it's interesting with technology of Google Earth to zoom in on some of these things. So that's where kind of overview of pellet mills are. Next thing is we're looking at industrial pellet production in the United States. And if we look at this, it really looks like the US South, in terms of industrial, is going to be a big player. So we're sitting over here in 2013. So there's a shift there in 2012 to 13 of an increase in the South industrial and trend of increasing rapid growth in that kind of production. So here in the Northeast, 2011-12 pretty flat. 2013 a little bit higher, or projected. I think this is a projected number, and then it increases a little bit. But the one that increases the most is this South industrial. If we look in terms of global pellet production, there was approximately 18.3 million tons produced in 2011, with a capacity estimated at 35 million tons. So we start looking at different countries. Obviously, we have the top here, United States and Canada are the 2 highest producing countries of pellets. So in the United States, we're at about 4.7 million tons, 26% of the global production. And then you can see some of the European countries. Latvia, as you'll see later, has an aggressive policy for renewables, and they're at about 3% of the global production. And so, which means, if they're, when we start looking at importing to Europe or exporting to Europe in our case, you can see that the United States and Canada are going to be big players probably on that type of stage. If we look at 2010 and 2011 in terms of pellets and direct trade of biomass energy, so this is showing the different kind of biomass direct trade. We look at pellets make up a significant proportion once we start getting into 2010, 2011. In 2009, it wasn't quite as big. You can see ethanol was fairly large in 2008 and has kind of decreased a little bit. But pellets pellets increased a little bit, and it's expected to continue to keep increasing. 2012, we have data that suggests both U.S. and Canadian exports to pellets in Europe has and expected to grow. So we look at, this is data, we're obviously in 2013 now, but this is data from 2011, where we were at in the U.S. and Canada, and then there was a marked increase in Q1 of 2012 of pellets going to the European market. So the European market becomes a key player in our pellet industry. One on raw material and where we're going to get this raw material for producing pellets to supply to the EU. The one takeaway, I guess, from this graph is really this southeast US pine. So now we're looking at not residues, but you're looking at logs. So 2013, it's not that large, but as you can see, the production of pellets is expected to really increase in the southeast United States using pine log raw materials. If we look at the cost, so we looked at some of the markets, but the cost of manufacturing pellets in the United States were the higher costs. The Northeast typically or traditionally has had higher costs compared to the Lake States South and West. And we look over on the second one, that's really has to do, at least from what I can tell, from the wood resource. So this additional cost comes to play in terms of the wood and the cost of the wood material. So we're looking at more hardwoods that are being used for higher valued, value-added products as compared to the South. We're looking at more commodity type uses for lumber, for softwoods. So in terms of costs, in terms of prices that historically have been shown for the sale of pellets, this is historical trends of the southeast US. You can see we had a high in February to March of 2010, and then we had kind of a fluctuation and decrease, so some up and down cycles, and then starting at the end of 2010, a little bit of a slight increase. Just as comparison, I went up and looked at New Hampshire publishes a monthly report on delivered pellet prices, and they were at about $247 per ton of 75 to 80% hardwood pellets. So a little bit more in terms of the price for these hardwood materials in the Northeast as compared to what's being shown on this graph. In terms of pellet use and sales in the U.S., if we're looking at just the U.S., it's tied up in residential heating. So you can look at the Northeast has a high amount of use in residential heating as wood, or a decent amount, pretty consistent with the Midwest and West, whereas the South really doesn't have that high. Obviously, it's not as cold in the South. We have more of a demand for these type of materials in the Northeast. United States, here's some data I put off from a PFI conference. There's approximately 845,000 wood pellet stove. Demand's going to increase about 2.3 million tons annually, and this is 50,000 to 60,000 new stoves are projected to be installed. Excuse me. And natural gas pipelines and local wood supply might be influential factors. So if you're located somewhere close to a natural gas pipeline, then your use of pellets may not be quite as high as someone who's out in a rural, remote area and has a high wood supply. So last thing I'm going to finish up with is some renewable energy policies, and what I view being things that are driving the market for trade. So we're going to look at just briefly European policies and US policies and the increase in renewable, in this case electricity generation by type. So if we look at the renewables, some of these policies are driving what type of renewables we're using and even just the use and increased use of renewables. So if we're looking at about 2013 here in terms of biomass, you can see there's quite a steep increase up to about 2020 and then a slight gradual increase up to 2040. So this is just forecasts for the United States. So you can see there's this increased use of biomass where water or hydropower is fairly consistent. Wind increases a little bit, solar increases a little bit. So what are some of these policy drivers? So in terms of the United States, a lot of states have goals. So they have renewable portfolio standard or a goal. Sitting in West Virginia, we have a portfolio standard. Right now, if we look where we're at, here's what's required by these portfolio standards in terms of raw material, a biomass that we would need. And then as these increase, we use less of the surplus, or we have less surplus. But as we get out towards 2014, the requirement of use of renewables is we end up with a higher surplus. And the surplus is really because of technology improvements as compared to here. So we're estimating that by 2040 our technologies for producing biofuels will be better. So in West Virginia we have a policy, and it doesn't just have to be biomass, it can be all kind of other things. It can be alternative products like coal fines, use of those type of things. So it's not always these renewable things, can also have alternative fuels in there. So the EU and why we have are seeing this market to the EU increase. There's been a directive, a renewable energy source mandatory target by 2020, and it's really to reduce greenhouse gas emissions, and they target about 10% renewable in transportation. So if we look at, here's the projections or estimations of where people want to be at in 2020 for renewables in their portfolio. Latvia is at about 42% versus say the UK, it's at about 15% of their portfolio being from renewables. Okay, so the last one I'm going to finish off on here before I just give a brief overview of some research we have here is there's been interest in co-firing with wood to meet these standards and goals, particularly the torrefied wood that I mentioned before. You can see there's 10 plants listed here that are the largest torrefaction operations, and when they started up or when they plan on starting up, what their feedstock is. United States, we have 2 that are listed here. But there's a lot of issues in terms of using these materials for torrefied wood. You can see there's economics, energy, can we run all the time, how available is our feedstock. My area of focus is really this densification, process control, and consistency part. So I thought I'd end just a little bit of research on what's going on here with some of my students at West Virginia, and really looking at influence of hot water extraction and torrefaction of hardwoods and short rotation woody crops on pelleting properties. So we have a single pellet dye that we use to study compaction behavior in these materials. We do a lot of things on compaction energy. So we look at, this is red oak not treated, and what the compaction energy is required to make a pellet, and then we torrefy that same red oak to that same treatment level of particle size and moisture content, and you can see the compaction energy goes up quite a bit. So those are some of the challenges with torrefied material. You increase the price just because of the energy required to make pellets. Here's some recent data we got on miscanthus, torrefied miscanthus versus non-torrefied in terms of pellet hardness. So you can see Get a little bit increase in pellet hardness if we compare this one and that one once we torrefy it, which is good. A little bit more energy required. And then this was on yellow poplar, I believe, and looking at torrefaction levels of high, low, and with and without lignin added. And you can see that the higher torrefaction level in this case had a little bit lower hardness than the low torrefaction level. Those are just a few examples of the things we have going on here to add a little research context to this discussion. So with that, I'm definitely over the 40 or so minutes I think I planned, but definitely take any questions.
Yeah, thanks very much. That's great in terms of folks who are really interested in pellets, which happens to be the most common use of biomass feedstock right now. And as you mentioned, growing, I'm sure this presentation will be watched many times. As you know, we're recording it, so there's a lot of very useful information. So we do have a few questions here. If people can stay on a little bit past the hour, we'll get them in, and please type in your questions. And I'll start with Bruce, who asked if you could discuss a little more about the transportation costs to the EU from different parts of North America.
Okay, sure. I can attempt to do that. Like I said, my focus area in research, anyways, has been the densification and manufacturing. But from some talks that I've been to and people I've discussions with, it's really the South, has kind of an advantage in your location to, one, the raw material, and two, to a port in terms of transporting to Europe. So I think that's why we see this increase in the production of pellets going to Europe from the southern region versus, say, the northeast. But there are opportunities in the northeast, if you're sitting near, some of the Great Lakes or some other places. If you have a decent amount of raw material supply there, you can make that transportation logistics work. So the sea shipping isn't too bad. It's the truck shipping and rail, more so truck shipping to get your material to a port. So I hope that at least gives you some answer.
Yeah, shipping containing transportation is relatively cheap. That's why you wonder why it's being traveled so far, because it's so cheap. Another issue you didn't really mention is the sustainability issues from the forest management, which is a big issue for Europe. But anyway, that's for another discussion. So Zane asks, given your chart showing high levels of NS, nitrogen, sulfur, chlorine in grasses, can they ever get certified, and how? Also, why such a great range in those numbers? Obviously, Zane is interested in the grass aspects of pellets.
Sure. Yeah, and like I deal a little bit more with wood. I've started getting into some grasses. But I think through some pre-processing type applications, you can start reducing some of those levels. Recently did some torrefaction stuff, and I haven't went through and got the proximate and ultimate analysis data on there to see if those values actually went down. But I'm guessing at least some of those values should go down. So I think it's through kind of processing that there's some markets. The other market for grasses I see more maybe in terms of using these pellets for a different market, and maybe they're not heat. Maybe it's bioethanol, maybe it is a project with coal biomass to liquid fuel. It's compared to coal. We have a lot more favorable properties with grasses. So, maybe the market is different. And, where we don't, this is really, those markets were just those were values for heating with wood pellets.
Right. Okay. Gary Gilmore asks about the energy return on the energy invested, so the conversion efficiency of taking trees to pellets to the end use. Do you have an estimate of that energy efficiency?
Offhand, I personally don't. I can say that I've done a few feasibility studies and looking at taking chips, not necessarily pellets, but taking chips and taking those from a tree into a boiler to produce steam. And those, the economics behind that is fairly decent as long as you can keep that cost of the chips below about $50 per ton, so green ton. If you start getting below that with chips, then you have some problems. But a lot of people have been looking more at chips and running chips through boilers as opposed to pellets, and there's benefits of each. But the payoff period or energy return. Some of the feasibility studies we were doing, we could retrofit a boiler with pellets or chips and get about a 7-year return on investment there.
How about the energy, the energy used to make the pellet compared to the energy it provides at the end use? That's I think what he's really asking.
What he's asking, yeah. Yeah, I don't have a really good feel on that. It really, I guess it depends on a lot of variables in terms of what your moisture content of those chips are and your grinding and wood cost. But
okay.
Offhand, I can't give you a really good idea. Sorry.
All right, if anyone online wants to type any answers in on that, great. Okay, Kathleen asks about when you discussed torrefaction, you mentioned that the resulting particles are hydrophobic. Are they actually hydrophobic? Or is it more that the porosity of the particles is less than for untreated wood? Do you understand the question?
I think so. Yeah. They're not. So what I mentioned was there's claims that these materials become hydrophobic, but they really don't. If you look at some of the graphs that I have, they take up less water than non-torrefied wood particles or wood pellets. And a lot of it, when we do these tests, we end up kind of drying off the surface, so it's actually water that's being taken up, internal porosity in this case. So they're not completely hydrophobic, they just take up less water, and that has to do with the hemicellulose being driven off there, and hemicelluloses take up a lot of more moisture compared to, say, the cellulose, and obviously more than the lignin.
Okay, Gary asks about certification of the wood, which is a big issue in the EU because obviously the environmental concerns of harvesting conditions in the US. And yeah, Gary, there's a lot of interest. I sort of mentioned that. That's probably one of the most contentious issues with the huge surge in pellet demand in the EU is it coming from sustainable sources. So there's a lot of talk about how to certify that stuff.
Yeah, I've read up recently and looked at SFI certification versus FSC. I don't know, Mike, you might know a little more. I know Europeans typically stick more to an FSC type certification, or is that kind of changing, or they just want some kind of certification?
Yeah, no, they obviously are stricter, but they are, obviously all the pellets to have it certified from the south especially would be very difficult. So they're just looking for some kind of verification scheme. Obviously the more FSC, which is stricter, more environmentally friendly per se than SFI, well, I don't think they're going to require that, but they're going to be looking for something even maybe a little less than SFI, but at least some kind of certification. All right, Zane asks about the cost per ton of making a pellet, if you're starting with chips.
Sure. Give me a second. I don't have that right in front of me, but I do have.
Okay, while you're mentioning that, while you're looking that up, I'll mention our next webinar in January is on the economic impact of developing biorefineries. So how much jobs are actually created. Our speaker comes from Iowa State, where he's had a lot of experience looking at the economic impact of these corn ethanol plants, and he's done some work on the New York bioenergy schemes up there. So look out for that. And the one in February is relevant to this topic because Xander from the Forest Guild is going to be talking about best management practices, which gets into the certification of biomass feedstocks. And so what are the best practices for harvesting this stuff? Did you have a chance to find it? If not, you can email it to me, and I can email it to Zane and anyone else who can just drop me an email.
Yeah, if you could just send me an email on that. I do have it. Part of a one of the courses I teach. We have went through and calculated some of those costs. And I have costs on chips, and then if we add torrefaction to it, in-woods chipping, I think I have a different number on that versus at the mill chipping, things like that. So maybe if you sent me an email, I could figure that out a little bit better for you.
Okay, I see someone else typing, which we can go over a little bit here. I'll ask a question. You mentioned it really comes down to the species, not even whether it's hardwood or softwood, in terms of the pellet quality. So, any thoughts on these on willow or even poplar as for making pellets?
Yeah, some of the things, at least, we have a little bit of willow we're going to start looking at, but we've done quite a bit on looking at red oak versus poplar, and really what we're finding with the yellow poplar is at least I haven't.
Well, yellow poplar is different to the hybrid poplar.
And the hybrid, yeah. So
I'm talking about the short rotation stuff, right? Like willow and the hybrid poplar.
And the hybrid, so like reclaim, mine land.
Just this really fast-growing stuff. I mean, I'm wondering what the pellet quality would be compared to.
I mean, a lot of it's going to come down to, at least my thinking, it's going to come down to lignin content in terms of hardness. The one thing that there's been a little interest in, depending on where it's grown, what kind of, is it taking up different materials from the soil than it typically would. So if we look at short rotation woody crops on reclaimed mine land, is it pulling up and storing different chemicals than it typically would grown in a forest? So those could impact that. But at least here in my research, we just have started looking at some of this.
Right. Okay. Justin put some information on the chat box about the energy return for energy used. So, Gary, there's a website for you to look at. Thanks, Justin. And thanks, everyone, for participating. And thank you again, David, for your presentation. I think it's very informative and will be useful down the line. And hopefully we'll see everyone next month. Take care.
Thanks.